We will now start our technical session 2, and we are already 10 minutes late till now. Actually, Professor Arindam Bhattacharya, he has given a long and important talk in the first session. So it is very tough to him for giving much time in his busy schedule. I am extremely grateful to him for giving time and chairing this session 2. So now I request to Professor Arindam Bhattacharya to chairing this session.
Okay, thank you, Prabir. Now I have to chair a session where my brother Gopal Chandra Seth is now will give lecture. I'll just mention some of his credentials. Gopal is presently an associate professor, but he's going to be professor because yesterday he has faced the interview in mathematics department of Jadavpur University and visiting associate of the Institute of Mathematical Science, Chennai. He has completed his master degree from the IIT Kharagpur in 2001 and PhD degree from Jadavpur University, Kolkata in 2008 in the field of biofluid dynamics. He has received several prestigious awards and honors, including Young Scientist Award, that is Boy Scout Fellowship, a very prestigious honor. In 2010, awarded by DST, Government of India, and visited University of Paris, France, for postdoctoral research work during 2010 and 11. Received Best Paper Presentation Award in the section of Mathematical Sciences awarded by Indian Science Congress Association in 2007. He has also visited UK, Spain, and Germany for academic purposes. He has also visited Indian Institute of Science, Bangalore, for postdoctoral research, for which the fellowship was awarded jointly by IASC, INSA, and NASI, Government of India. He has published more than 85 research papers in reputed international journals, in Elsewhere, Springer, World Scientific, Wiley, InterScience, Taylor and Francis, Hindui, etc. Publication house. He has produced 7 PhD students, and many of doing now. He has completed 7 research projects sponsored by DST and UGC. His research interests include biofluid mechanics, microfluids, and nanofluids, boundary layer problem, MHD, CFD, heat and mass transfer, and bioheat transfer in the living tissues. So now title of the talk is Peristaltic Flow of Physiological Fluids. So I request Gopal to start his lecture. I think you will enjoy his lecture because it is very much related with our modern world. Okay, so start, Gopal.
Okay, thank you, Professor Bhattacharya, for introducing me. So let me go to the presentation. And good afternoon, all of you. At first, I would like to thank Professor Prabir Gharami and Professor Vasudev Dhara and all the members of this organizing committee for inviting me to share some knowledge of my research fields. As the participants are mainly from the college students, so I will not go into the depth insight into the research problems, but I will say something about the research problems, means how to construct the research problems, how to solve it mathematically, and also how to present research results. I hope this might be useful for the college students for their further career in the near future. I think so. I think my screen is visible to all of you.
Yes, yes.
Okay, so so I'm just starting my presentation. Okay, So today I will be talking about the peristaltic flow of physiological fluids. So as you know, the peristaltic flow, it's a mechanism of fluid transport. And this phenomena or mechanism is mainly observed in the physiological systems. So I will explain those things today. So for my presentation, simply I will say something about the introduction of this problem or this topic on this topic, and then how we can model the problem and how we can solve the problems and their results. I'll show you, and also some references, important references. See, as I told, the peristaltic transport, as you can see in this picture video, maybe you can look onto this and then I'll explain. So peristaltic transport is a mechanism of transporting fluid, mainly physiological fluid, and that is mainly induced by the propagation of waves, progressive waves, of course, with area contraction and expansion along the length of the tube containing fluid. You can see in this picture the some amount of fluid is moving towards by contracting and expanding the tube, and some amount of fluids you can see it's trapped and moving forward with the wave speed. So all those things I will describe now. But for this problem, this peristaltic mechanism, first this idea presented by Latham, who presented this concept in the thesis while he was the student at MIT, USA. And after that, many scientists, they studied on this problem experimentally as well as theoretically, and successively till now it's developing this phenomena. And this peristaltic phenomena mainly observed in the physiological system. So this is one of the example I can show you. On the left side, you can see it is actually the esophagus, means the food, so whatever we are eating, that is going from mouth to the stomach, okay, through the esophagus. So this is the tube, okay, and this is the food bolus and food. So you see, when we eat something, so there is no driving force, okay, so there is no force we put to push down the food into the stomach. But when we eat it, automatically it reaches to the stomach, and the food bolus, the form of some food that comes to the stomach by this peristaltic mechanism. How? By area contracting and expanding. So this is basically the neuromuscular property. So by this neuromuscular property, so the food bolus through esophagus that comes into the stomach. So the left hand side, this is actual the physiological system. But when we do some mathematical model, so it is difficult to define the geometry of this irregular shape. Okay, so it is very difficult, but we can approximate this geometry into some smooth function, so that this esophagus or this kinds of the phenomena we can approximate it on the right side, that is by some smooth tube, and the same mechanism we can find, and then we can study a lot mathematically on this topic. So not only that, the peristaltic motion mainly finds in many applications. So these are the few, although I have listed, but not limited. So the peristaltic mechanism, this is observed in the urine transport from kidney to the bladder. So the urine flow from kidney to the bladder, that is due to this peristaltic mechanism. The movement of chyme into the gastrointestinal tract. The chyme means partly digestive food or some acidic food like that, and the movement of those foods to the gastrointestinal tract, that is also due to this neuromuscular property, means peristaltic motion. Fluids into the lymphatic vessels, bile, movement of bile from gallbladder into the duodenum, spermatozoa, movement of spermatozoa sperm in the male reproductive tract, and the movement of ovum in the fallopian tube, and also very important, that is the circulation of blood in small blood vessels. Okay, so in the small blood vessels where the pressure is very less, means actually blood flow from heart to the whole body. That is because of the contraction and expansion of heart. Okay, means the pumping action of the heart, and due to this blood means transport to the all body. So where the pressure gradient is very less in the case of the microvessels, so then the blood is flowing through this mechanism also. So not only that, this peristaltic mechanism also finds in many industrial applications also for the development of many medical devices. Not only that, in many engineering applications also, like a roller and finger pumps, and some biomedical instruments like a heart-lung machine, artificial heart-lung machine, blood pump machine also, and dialysis machines. Okay, are also developed on the basis of this principle. So in this picture, you can see the some amount of fluids are coming, and it's making trapped in area contraction, and because of this expansion, some fluids are going through this. Okay, so this is another example of the peristaltic mechanism. So, so how we can model this mechanism into our real life problems. So before going to that in details, let me define two keywords, two important words. One is called the reflux and another is called trapping, because these two things are very important phenomena associated with peristalsis. The reflux means, as defined by Shapiro in 1969, it refers to the presence of fluid particles that move on an average in the direction opposite to the net flow. So when the some amount of fluid mainly transport in the forward direction, but because of this area expansion and contraction, some amount of fluid moves in the opposite to the net flow. Okay, so that means we can say that the negative flow that is defined to be, as we'll henceforth we'll call it a reflux. And the other one is the trapping. Trapping means at high flow rates, the large occlusion means some blockage are there. It's a region of closed streamlines, and in the wave frame, some fluid is found to trapped in a wave of propagation, and this trapped fluid means the form of the football, as we can say, is found to move with the mean speed equal to the wave, and that will move forward. So the reflux and trapping, these two are very important phenomena. We can study a lot. So when we study any research problem, so this is necessary to know the development of the research in a particular field. So, so we need to see how this topic has been developed, and until now it's developing. It started in 1966, Latham, who initiated this mechanism of peristaltic transport. And then Ian and Feng, Y.C. Feng, just last year he died. Okay. In 1971, he compared their results, they do some experiment, okay, and compared those experimental results with the theoretical results obtained by Latham and many others, and they come into the conclusion that so the peristaltic mechanism that we study mathematically, that is very much correlate with the experimental work. And after that, many theoretical works on this is going on. Many researchers, they consider initially the fluid to be Newtonian fluid. So actually the fluid we categorize into two types. One is called a Newtonian fluid, other one is a non-Newtonian fluid. So the Newtonian fluid means when the viscosity is very less, means when the shear stress is linearly proportional to the shear rate. So those fluids behaves as a Newtonian fluid, and they have studied. But later on, Stokes in 1966, not later on. Before that, they have started this peristaltic transport using coupled stress fluid, and that is a non-Newtonian fluid, where the particle size effect can be taken into account. And then successively in 1969, 1986, on this coupled stress fluids, and the people, they have started by considering blood as a coupled stress fluid. And then also in 2008 and 2011, the many theoretical works have been done, and then they tried in 2011, they tried to apply some magnetic field if on the blood vessels, because the blood cells contain hemoglobin, which are basically the form of iron oxide. So the magnetic properties are there, so blood flow can be affected by the application of magnetic field. And then myself and my students tried to find those mechanisms in the blood vessels. If we apply the magnetic field, mainly in most of the cases, they have neglected the induced magnetic field. But we have incorporated all those things to see, even there is small changes, but how the small changes, small approximation in the model, how it can behave as the large changes in the results, we have tried to show. And then the several papers we have made in these years, so till now continuing. So it is still developing field. So as per the mathematical model, so as I told, the Newtonian fluid model is the viscosity is very less. So that means the shear stress tau is linearly proportional to the rate of shear rate del u del y velocity gradient. And based on this principle, the constitutive equations are given by this is in two-dimensional Cartesian coordinate system. So this is the continuity equation to preserve the conservation of mass. So while we studying the fluid flow in a particular domain, so we keep the fluid mass to be conserved. So there will not be the mass will vary at any time. So we need to solve the momentum equation together with this continuity equation or conservation of mass. And these are the two the equations of motion. We call the momentum equations of motion in two-dimensional Cartesian coordinate system. On the left-hand side, okay, so this represents basically the fluid acceleration. So mass into fluid acceleration equal to the total applied force, as we know from the Newton's law of rate of change of linear momentum. So the mass actually is rho, and there is some volume. We have neglected it for integration. So there's a mass into acceleration on the left-hand side, and the right-hand side the total force. So this is external body force, and this term is your pressure gradient force, and this term is the viscous force. Similarly for the other equation. So these are the partial differential equations, and of course they are coupling partial differential equations. So we'll solve these problems. So it is not easy to solve these problems. Till now, there is no analytical solutions available to these problems. Because of the non-linearity on the left-hand side, you can see these terms are the non-linear terms, the product of u, the product of the unknown function u and del u del x are there. So this makes this equation non-linear. So it is very difficult to solve analytically. So for that, the people, what they do, generally, they try to simplify those equations so that we can solve this mathematically. But the negligence of those terms is always not good. So then after that, the people, they are solve those problems numerically by keeping all those terms to get the good results. But still, if we even neglect those things under certain conditions, I will explain again, under certain conditions, but the results are also valid. And the other kinds of fluids are mainly non-Newtonian fluids. Actually, the other, I will not show much about the mathematics of the non-Newtonian fluid, but these are the examples of some non-Newtonian fluids like a power law fluid, Herschel-Berkeley, Peristaltic, microfluid, coupled stress, and many things. Because in this case, non-Newtonian means when the shear stress, this is the shear stress tau, is were not linearly proportional to the del U del Y, the rate of shear. So as from this figure you can say, so this is the linear relation between the stress and the rate of shear. So that's why the Newtonian fluid, they follow this linear relationship between this. But if they are like this, if these are the nonlinear curves you can find, so this represents the non-Newtonian fluids. They are either pseudoplastic fluid, this is example of blood. They may be dilatant fluid like sand water, means water mixed up with sand. That is the Newtonian fluid, may be treated as a dilatant fluid, you can say. And the example of Bingham plastic or plastic fluids like you can say toothpaste. So this is the example of Newtonian, non-Newtonian fluid, okay? Or the tomato sauce or tomato ketchup, so these are the examples. Or, not only that, drilling mud, okay, chocolate, okay. So these are all examples of non-Newtonian fluids. But the blood also may be treated as a non-Newtonian fluid with certain conditions. So maybe the pseudoplastic or blood plasma may be taken as a Newtonian fluid, and also sometimes the blood can be represented by this Bingham plastic fluid when the blood cells, the concentration of blood cells is more. So then the blood may be treated as a highly nonlinear at a low shear rate. Okay. So these are the Newtonian and non-Newtonian models. You have some idea. So depending upon the problem, so where you are working, so what kind of your fluid is there. So depending upon your type of fluid, you choose the corresponding model. Either we'll choose the Newtonian model or we'll choose the non-Newtonian model. So this is the first step, to choose the model and then your problem. So this is one of the problems where this is the fluid flow through a tube, where the tube wall oscillates like this, the area contraction and expansion, and the amount of fluid that moves towards z direction, the positive flow direction, with the wave speed c. And so this is we can mathematically express by this geometry. So this is basically a cos 2 pi by lambda z minus ct. So this is a good example of progressive wave. Okay, so if we use this mathematical form, progressive wave, okay, so that can generate this geometry, and within this geometry we can study the fluid flow phenomena. Okay, and these are called the crest point, and this is called trough point. So the distance between two troughs, consecutive trough, this is called the wavelength, or maybe from here to here, this may be defined as a wavelength. And this d, this is the constant radius of the tube, you can say. And d plus minus some amplitude, this is the amplitude of this. So this must be d plus minus something. But this is only the, I have put this geometry for this, but for the whole geometry, the upper wall or lower wall may be defined by like this way. So this is the another example of the tube or channel where it is bifurcated. So that means the channel walls varying with angle, it is not parallel to x-axis. So its geometry can be like this way. And so as an example, here we'll consider unsteady and fluid is incompressible, means density will not change by the change of the volume of fluid or the pressure. And this is, we consider the viscous and also electrically conducting fluid, where we can apply the magnetic field. So blood is a good example of electrically conducting fluid, and we choose the coupled stress fluid model. So this is one of the non-Newtonian fluid model. We have chosen this problem because it takes into account the particle size effect. So within the blood we have many blood cells, red cells, white blood cells, and the platelets. Okay, so many blood cells are there, so their size may be different. So if we use the coupled stress fluid for the blood model, so we can capture the size effect of all those cells. And also we have assumed the channel to be asymmetric, means in the next slide you can see. So this is the channel where the channel height, means the center line may not be always on the middle of this channel, and the walls, they not may move equally with the upper and lower wall, so it makes some phase difference between the waves. So this is the equation of the upper wall, d1 plus a1 cos 2 pi by lambda x minus ct. This is the example of progressive wave. And the lower wall moves with different waves, so that means there is some phase difference with these two equations, so pi is included. So maybe this is the better geometry where it is not actually the regular, so asymmetric channel we can make it. So this is first the construction of geometry, where we'll study the fluid flow, and we have seen how we can choose the fluid model. So then we'll construct the governing equations. We'll choose, this is written in vector form, although, but not, I could not get to type all those equations in simplified form, but so this is written in vector form, divergence of preservation, mass conservation, continuity equation, and this is the momentum equation for the coupled stress fluid. As usual, this is as I displayed. The left-hand side, this represents the fluid acceleration on convection, fluid convective term, pressure gradient, and this is the viscosity, viscous force, and this is the force due to the coupled stress effect. Okay, that takes into account the particle size, and this term is basically the Lorentz force, and the Lorentz force arises due to the application of magnetic field to the electrically conducting fluid, and the magnetic field is generally applied perpendicular to the direction of flow. And the last term that takes into account the inclination of the channel. So all time the channel may not be the horizontal or vertical, or maybe in any angle it may be. So we have modeled those problems by taking into account all those things to make it more realistic. And as you know, in the fluid mechanics problem, so always we try to present the results. Those results are independent of the choice of the dimension. So first we would like to make all the variables, means dimensional quantity to non-dimensional quantity by using some characteristic length or velocity. So the x length, the distance, x distance is dimensionalized by the wavelength, because wavelength we know, and also the y direction is dimensionalized by the fixed radius of the channel, and so on. These are some non-dimensional quantity, and these are some transformation. So from the wave frame of reference to the laboratory frame of reference to convert it. So we choose this transformation, and while we use all those non-dimensional variables, if you substitute those into the governing equation, these are written all in dashed notation. Okay, so this means these are in dimensional form. So when we convert it to non-dimensional form, so then the equations involve some non-dimensional parameters. So like this is the Reynolds number. As you know, the Reynolds number is a non-dimensional number which is defined in this problem is like this, but this is basically ratio of the viscous force to the inertia force. And this is the wave number delta, defined to be the ratio of the height of the channel to the wavelength. And this is the coupled stress parameter, and this is the magnetic field parameter, means we call it a Hartmann number. So B0 is the constant magnetic field we apply. Sigma is the electrically conducting fluid, mu is the fluid viscosity, and D1 is the constant radius. And this is the Prout number that takes into account the inclination of the angle with the horizontal axis. Okay, so when you substitute all those things in the governing equation, and if we extract them, so these are the equations we can find that they are written in non-dimensional forms. And you see in this governing equations, the some non-dimensional parameter that appears, Reynolds number into delta, means the wavelength. Okay, and also here the Reynolds number by Prout number, and 1 by gamma, say coupled stress parameter. Now you see, So our problem is such that means we are studying the blood flow through small blood vessels. Okay, so in the small blood vessels, the blood flow is very slow. So the slow motion is there. As the fluid motion is very slow, we can think it's laminar, and the Reynolds number is very small. Reynolds number, because we have seen in the definition, Re is defined to be U into L by nu. U is the average velocity into the length or maybe the radius of the tube by the viscosity. So the blood flow in the small blood vessel, that makes this Reynolds number is very slow, means the slow motion. And delta, that is d1 by lambda. When lambda becomes large, means we assume that the variation of the walls, tube walls, are very slow. So that means the wavelength is large. So if wavelength is large, then the wave number delta becomes very small. So the Reynolds number and the wave number delta, this product makes it also so small. And as the delta are small, so the delta square and delta to the power 4, these are also small. So those small quantity, okay, so these terms are very small in comparison to the others. So hence it allows us to neglect these terms. If we neglect these terms in comparison to the pressure gradient or the other terms, so it will not harmful. So we can neglect these terms very easily, means by assuming delta square is very small and Re unit delta is very small. Similarly for this equation also, okay. And because these are the two set of partial differential equations, system of partial differential equations, so it's coupling each other. It is very difficult to solve analytically, but here we are trying to find the analytical solution. For that, we can do another technique. We can convert these equations of motions, okay, into a single equation of motion by considering this transformation. Means we can transform these equations in velocity form to streamline. Okay, so we can convert this equation into the form of streamlines. So the streamlines, as you know, the streamlines means a curve. Okay, at each point on that curve, if we draw the tangent, so the tangential direction coincides with the velocity of the fluid or the velocity of the particle. Okay, so this streamline can allow us to see the flow phenomena or the flow pattern we can observe if we see the streamline. So it is easy to convert those equations into a single equation, okay, by neglecting this pressure gradient. If we cross differentiate, if we differentiate this with respect to y, and if we differentiate this equation with respect to x, and if we subtract these two, so then accordingly other terms will change, and we can substitute u equal to del psi del y, v equal to minus del psi del x. Okay, then it makes a single equation in terms of stream function. But it is, you can understand, so this equation involves a fourth order derivative of the u or v, but the Newtonian fluid, that involves the second order derivative. So this equations will give you more information than the Newtonian fluid, and also it is difficult to solve these equations. And when we solve this partial differential equation, means when we construct a research problem, the problem must be well posed. As you know, the well posed problems defines in three things. First of all, the solution to the problem must exist, and the secondly, the solution must be unique, and third condition is that the solution must continuously depend upon the initial data. So the initial data means we can say here in terms of the initial conditions and the boundary condition. So when we solve any physical problems, mean that is in the form of the partial differential equation, governing equation, and these equations are developed from on the basis of the law from the law of physics. Okay, and we convert the law of physics into mathematics, and then we'll solve those mathematics. Okay, so we must provide some boundary conditions. So although maybe these are complicated, but you can think this is u plus beta del u del y. So we have imposed some people, they use of the no slip condition. No slip condition means U equal to 0. The tube wall they assume to be rigid, but this is not, as the wall moves periodically. So the wave motion is there, so the blood vessel cannot be treated as a rigid wall. So we cannot put the no slip condition U equal to 0. So we must consider the slip boundary. Slip boundary means at the interface between the solid and the liquid. So there is some the slips means one layer dominate the other layer. So there is a interaction between the solid and the fluid, okay, solid boundary and the fluid or liquid, okay, and that is the velocity U can be taken as the gradient of the velocity gradient. So, and if we substitute U equal to del psi del y, so these two equations takes in this form, and beta is called the slip length, okay. It has also more phenomena. Slip length means on the wall it is not exactly 0, okay. If beta is 0 means the slip wall. So if you put beta equal to 0, then you will get U equal to something, okay. So, and then we have used some vanishing couple stress. We assume that on the wall the couple stress vanishes, and also we assume that volumetric flow rate at the wall psi is equal to pi by 2 and psi equal to minus pi by 2. As you know, if we consider the difference between the streamlines at the 2 points, okay, on the curve, and that gives you the amount of fluid passing through that curve. Okay, so if you take these two difference, that will give you psi equal to F. Okay, so F is the flow rate, means amount of fluid passing through a particular cross section of the channel. Okay, so based on these concepts, so we can construct the boundary conditions. We can assume like this. So the governing equations, okay, that has transformed to the single equation in the streamline. So this is the reduced equation, okay, and of course this is 6th order partial differential equation in psi, and these are the corresponding parameters. So we'll solve this differential equation together with the boundary condition. So now it becomes easy to solve this differential equation. So for that we have assumed the solution matrix in this form C1 plus C2y plus C3, etc. Just you can find using some auxiliary equation as you solve in the case of ordinary differential equation like this. You just solve it and find the psi. And C1, C2, C3, C4, C5, and C6, these are all constants arising out of these equations, and we can solve these constants with the help of boundary conditions. That's all. If you solve those constants, so your solution is now in your hand. So then you can present your results. And once you find psi, then it is possible to return back to your velocity components by using U equal to del psi del y. If you differentiate psi again, you with respect to y will get U, and also V minus del psi del x, okay, and you can get those velocity components. And also again, if you substitute back in the governing equation, it is you can find the pressure gradient, expression for pressure gradient. So you can substitute this U from here, you can substitute all those things, but for the sake of simplification, I have not presented all those C2, C3, C4 because they are very complicated and large expressions, so I have not presented, but those are all functions of x, okay, independent of y here. And then it is possible to find del P del X pressure gradient, okay, and you can find the behavior of the pressure gradient by changing the inclination of the angle, by changing the particle size, by applying the different magnetic field, and so on. And also you can control your flow rate, and then you can see the how much pressure gradients involved in a particular location, and actually the pressure rise per wavelength we generally calculate for better representation of the result. The lambda that represents the pressure rise per wavelength means we integrate this pressure gradient per wavelength 0 to 1 in the XL direction, so that you will lambda. And the other things we can also determine. So once you find the solution of the governing differential equations U and V, so then it is possible to find the other factors. Maybe I have not calculated here. Other factors, this is one of the factor, pressure gradient. Okay, the other factors may be the skin friction, means the friction of force, okay, imposed on the wall, and also you can find the volumetric flow rate, how the flow rate changes, okay, and the other things. So many quantities you can study. But here I have only the velocity profiles we have seen. You can see on the left hand side, okay, and so this is the reflux, okay, as you have told, reflux, that means when the fluid moves on an average opposite to the direction of the net flow. So in this case means there are some particular locations at the area of the behind the area of the contraction, and this is in front of the expansion. So on the behind of the contraction, the fluid becomes in opposite direction, the negative flow becomes, and this is the different values of H, means B0 magnetic field strength, and we have seen that if we increase the magnetic field strength, so negative flow rate can be removed like this way. And also this is in other particular location, the axial velocity, if you apply the more magnetic field strength, so so in the central line of the channel or tube, the main flow rate reduces, but near the wall the fluid increases, because to conserve the flow rate in a particular location, the mass should be the same. So the fluid at the central line it decreases, but near the wall it is increases, okay, to preserve the mass or flow rate, we can say. So these are the examples how we can present our results, okay. So these are also some other profiles, okay, for different magnetic field strength, and this is the beta means slip length, okay. So slip length also play an important role. When the slip length is very small, the fluid is more faster. If the slip length becomes more high, so then the velocity becomes slower at the central line. And these are the pressure gradient you can see along the x-axis. So that means this is the expanded region, and these are the contracted region, you can see. So in the expanded region, more pressure gradient is needed, okay, to transport the same amount of fluid, whereas in the contraction region, less pressure gradient is required. And similarly, these are also the effect of the coupled stress parameter. If we increase the coupled stress parameter, so the less pressure gradient is needed, and these are the result phenomena. And also this is the result you can see due to the change of the phase difference, okay. If for phi equal to 0, so then it is of the almost symmetric, as I shown the previous result, those are phi equal to 0. But if phi is non-zero, if there is a phase difference, so the pressure gradient they vary like this way. So that means the less amount of
I ended my speech, thanking and regards.
Okay, thank you, Momita, for sharing your views. Any
Thank you,
other
sir.
from outside?
Good,
Yeah.
good afternoon, sir.
Okay, Rashbi, are you?
To all share my experience. As I am present here, we feel very happy and proud for organizing such an international webinar by the Department of Mathematics, Birla College. As a student, this is a very proud moment for us. I learned the advanced portion of mathematics. It was a great opportunity to listen honorable dignitaries, research person. They discuss about their research paper and their knowledge, and really inspired a lot. The whole session was the complete learning experience. which will help me in my future. Uh, I request my teacher and honorable speaker to organize such types of webinar in our college campus in another topics like how to tackle real life problem with mathematics or recent situation and future mathematics student after pandemic situation. Lastly, I would like to thank my college for giving me this opportunity to explore more, be more careless and adapt to change better. Thank you, sir.
Okay, thank you for your good suggestion that the relation between mathematics and real life, we should do another conference, like Pravid may take the responsibility. Any other participants? So if not, Basudev, will you finish or Pravid?
I say few words and after then you will finish. I am really happy that our student has understand something. This is our aim, that students should learn from this international webinar. Otherwise, it will be not fruitful. Since some comments has come here that student has understand and they have enriched. So I think our aim is successful, and many speakers and they have discussed from different field. For the Probir has arranged that all these speakers, eminent speaker. So I am grateful to Probir also, because Probir has our newcomer, new faculty joined few days back, and after joining, he has arranged enthusiastically. So different from different field, all these speakers he has arranged. So I am really proud of him. So Probir is very much enthusiastic, and he has done this thing. And this speaker, Professor Manos Pratim Das, has told very interesting topics of history of mathematics, and Professor Haidar Ali Biswas, he has talked about mathematical biology and present situation, how to tackle the pandemic situation, and how to reduce this COVID-19. He has spoke very interestingly in this topic. Present, it is very much relevant. And Professor Vivek Kumar Sadhu has spoke about algebra, and Gopal Chandra Sit is my friend also. He spoke about fluid mechanics, and Professor Kaushik Ghosh has spoke about very interesting topic, astrology and astronomy. I am very much interested in this topic, and from I know that from ancient time, the people first had to study first astronomy, and from there, after few days, from astrology, astronomy divided two part, astrology and astronomy. So now astrology is not a science, but astronomy is a science. So it is very interesting topic, and student has to know very well what is astronomy and astrophysics, what is science. Otherwise, student will go to astrology. Why they have uh, why they are they when they will have some exam, they will go to astrologer. So no, astrology is not a science. So I think very interesting topic Professor Kaushik Ghosh has talked about, uh, and Professor Orindam Bhattacharya has spoke about mechanics, about and very interesting topics also. And Professor Orindam Bhattacharya is very well known to me. When I did refresher course, you are the refresher course coordinator. So I know you very well.
Oh, okay.
And
Forgot now.
anyway, so I would like to thank you all. So sir, you finish it. You say few words, and then
Okay.
and if Professor Kaushik Ghosh want to say something, or Professor Gopal Sit, if you want to say few words, then you can say.
Kaushik, will you speak something about this conference?
Yeah, okay. Am I audible?
Yeah.
Yeah,
Yes, sir, yes.
yeah. Let me first thank the organizers, all the faculty members in the Department of Mathematics, and the principals are also in Belda College for organizing. I think in the very short time notice, they have organized this beautiful particular webinar. So I should congratulate them, of course, from the very deep of my heart. And as I have actually experienced 2 days, not of course, I cannot tell you that I have not covered the entire time. I was absent at the first half of yesterday. But anyway, I covered 4 different lectures, including myself, of course. And in that aspect, I can tell you that the topics they have actually chosen, that is it actually covers a different range of pure mathematics, applied mathematics, as well as applicable mathematics, as Dr. Dhara has already mentioned, that it has actually a diversified range of topics in being covered in the sense of all the speakers topics. And of course I can see that they have beautifully organized this one, divided in the form of the Google Meet as well as in the YouTube link. They have provided the platform to actually accommodate more number of participants in this particular webinar. So thanks to them. And of course, one student has mentioned that in recent days, of course, you can organize one particular webinar or workshop or even maybe conference on the applicable part of mathematics in real life. That is very interesting one. And I will suggest only the organizers, if possible, in future, within the virtual meet, if possible, you can try to organize one day, might be one day, very short conference where some of the contributors can present their actually the presentation, and 1 or 2 or 3 invited talks may be there. That will be more interesting and actually beneficial for the other participants also. So thank you again to the organizers for arranging this particular webinar in a beautiful manner. Over to Professor Arindam Bhattacharya.
Okay, thank you, Kaushik. Now Gopal is here. Gopal, will
okay. They have told many things. Okay. So at first, I would like to thank all the faculty members of the Department of Mathematics of Belda College. So I'm really grateful that they have organized
Now I give a vote of, this is the session for vote of thanks. I speak out some words for the audience, respected speakers and organizer, all to all. I want to give some give thanks. I am starting now. Honorable Professor, our beloved principal, and our valued invited guests, it's my privilege to propose a vote of thanks in this webinar. I, on behalf of Department of Mathematics, Belda College, and the entire team, placing your important work and sharing with us your findings and opinions. A big thank to Dr. Manas Pratim Das, program producer of All India Radio, Kolkata, for his detailed and enriching topic on the history of mathematics. I must mention our deep sense of appreciation for Professor Arindam Bhattacharya of Jadavpur University, Kolkata, for his interesting lecture on geometry. Further, we are grateful to Dr. Haidar Ali Viswas his knowledge on mathematical biology. I may like to express our sincere thanks to Dr. Kaushik Ghosh of Bardwan University for giving an excellent coverage on astrophysics. I also wish to Dr. Vivek Sadhu of IISR Bhopal for his analysis. And last but not the least, I would like to acknowledge our gratitude to Dr. Gopal Chandra Seat of Jadavpur University, Kolkata. I would like to take this opportunity to place our hearty thanks to our principal for the perfect support of his guidance he has extended to us. I also extend my thanks to our convener, Dr. Probir Gharami, joint convener Vasudev Dhara, and our coordinator Shahjahan Sheikh. We also very grateful to the computer department of our college for the technical support.